Have you ever been sitting in class, fighting to stay awake, and suddenly your brain decides it's nap time? Maybe the teacher is droning on like a robot, or you stayed up scrolling on TikTok all night. But for people with narcolepsy, this can happen even if the teacher is cracking jokes and doing car wheels. Narcolepsy is a neurological sleep disorder involving a reduced ability to regulate the sleep wake cycle. This rare disorder affects about 42 out of every 100,000 people, and individuals report feeling many symptoms such as excessive daytime sleepiness, cataplexy, sleep paralysis, disruptions in sleep, and insomnia. Because of this, it becomes really difficult to stay focused and alert. Narcolepsy is marked by a wide variety of symptoms. A core symptom of narcolepsy is extreme daytime sleepiness. Even if individuals get a sufficient amount of sleep at night, they experience an overwhelming and constant urge to sleep throughout the day. In many cases, people with narcolepsy can fall asleep abruptly, which can make life challenging, difficult, and even dangerous. Another symptom of narcolepsy is abnormal REM sleep patterns. People with narcolepsy can enter REM sleep in as little as 15 minutes, whereas most people don't enter REM sleep until about an hour to an hour and a half. Another symptom of narcolepsy is sleep paralysis. People with narcolepsy can have episodes where their body can't move. This usually happens right when they're falling asleep or when they are waking up. During these moments, the person is typically conscious. Another symptom of narcolepsy is insomnia. Individuals with narcolepsy may struggle to fall and stay asleep. This often leads them to experience fragmented sleep. Cataplexy is one of the most unique symptoms of narcolepsy as it only occurs in narcolepsy type 1. Cataplexy involves a sudden loss of muscle tone and is typically triggered by intense emotions. Interestingly, these episodes are most commonly triggered by positive emotions. However, negative emotions can also trigger cataplexy. Narcolepsy can be divided into two major forms, type 1 and type 2. Both share many of the same symptoms. However, type 2 narcolepsy lacks cataplexy and generally has normal cerebrospinal fluid erection levels. Additionally, much of its neuropathology remains unknown. Conversely, the mechanism behind type 1 narcolepsy is far more understood. It is defined by the loss of orexin producing neurons in the lateral hypothalamus. For the purpose of this video, we will focus on the neuropathology of narcolepsy type 1.
As previously mentioned, it is the loss of orexin or hypocretin producing neurons that causes the symptoms of narcolepsy type 1. Hypocretin neurons are found in the lateral hypothalamus and project to arousal and emotion-related areas where they stimulate neurons to release neurotransmitters that maintain wakefulness throughout the day. For some background information, the brainstem is made up of the midbrain, pons, and medulla oblongata, which together form the main connection between the brain and the spinal cord. It is organized into three key anatomical regions: the tectum, the tegmentum, and the basal area. Hypocretin neurons project to various structures in the tegmentum that are involved in wakefulness. These structures include the locus coeruleus, the dorsal raphe nuclei, the pedunculo-pontine tegmental nuclei, and the latero-dorsal tegmental nuclei. Other structures that hypocretin neurons project to are the tuberomammillary nucleus and the basal forebrain. In a healthy individual, wakefulness is maintained by hypocretin neurons exciting each of these structures, allowing them to signal to other areas of the brain via different neurotransmitters. Wakefulness and arousal occur when excitatory input is received by the cortex from these structures. A major component of this cortical excitation comes from the ascending reticular activating system. This is a network of neurons that relies on collaborative activity between the cortex, thalamus, and reticular formation. It has two main routes: the dorsal route, which projects from the reticular formation to the thalamus and then the cortex, and the ventral route, which projects from the reticular formation to the hypothalamus and then basal forebrain. For maintaining muscle tone, there are two other important structures: the ventrolateral periaqueductal gray and the lateral pontine tegmentum. The ventrolateral periaqueductal gray and lateral pontine tegmentum primarily act to keep the REM system off, ensuring you don't just doze off in the middle of the day. The VLPAG and LPT receive hypocretin input from the hypothalamus. They then send GABAergic inhibitory signals to the sublaterodorsal nucleus, or SLD, which is the REM atonia center in the pons. This ensures that the SLD cannot activate the ventromedial medulla, which usually signals to the spinal cord. The ventromedial medulla cannot excite the inhibitory spinal interneurons, and as a result, the muscle tone is preserved while awake. It is important to note that the amygdala, which processes strong emotional stimuli, can inhibit the VLPAG and the LPT. Under normal circumstances, hypocretin input counteracts this amygdala inhibition, maintaining SLD suppression and preserving muscle tone even during emotional experiences. In narcolepsy type 1, destruction of hypocretin neurons in the lateral hypothalamus removes this excitatory stabilizing input. Without hypocretin, the structures it excites are less active and there is less cortical excitement, leading to unstable wakefulness and excessive daytime sleepiness. Simultaneously, the VLPAG and LPT are more easily inhibited by emotional input from the amygdala, allowing the SLD to become active during wakefulness. Activation of the SLD then excites the ventromedial medulla. The ventromedial medulla excites the inhibitory spinal interneurons, which results in a sudden loss of muscle tone. Loss of hypocretin therefore destabilizes both the wake-REM switch and the REM atonia gating system, explaining the core symptoms of narcolepsy type 1.
While there currently is no cure for narcolepsy, it can be controlled with medications like modafinil. Modafinil is a wakefulness-promoting medication that is commonly prescribed to individuals affected by narcolepsy to treat the symptom of excessive daytime sleepiness. While its mechanisms are not fully understood, research has shown that it acts by blocking dopamine and norepinephrine transporters. As a result, levels of dopamine, norepinephrine, serotonin, histamine, and glutamate increase, while GABA, which is an inhibitory neurotransmitter that normally promotes sleepiness, decreases. So when someone with narcolepsy suddenly nods off or collapses while laughing, it's not their laziness. It's hypocretin neurons in the lateral hypothalamus taking a vacation. Without these neurons, the arousal centers like the lucus coeruleus, dorsal raphe nuclei, and tuberomammillary nucleus don't fire properly, and the VLPAG and LPT can't keep the REM atonia system in check. The result? Excessive daytime sleepiness and cataplexy. By studying these brain circuits, scientists are learning how to restore balance in wakefulness and muscle control, helping people with narcolepsy stay alert and active, even during the most exciting or emotional moments.